Good morning to all the colleagues that are joining from Australia and New Zealand this morning. I'd like to introduce to you Gonzalo Mora and Christian Romero, who is doing the presentation for us for LVSIM-EMS software, the simulation software this morning. We have a series of presentations we're doing, webinars over the next few weeks. We hope you get good information from this one and join us for our ones for the future. I'll pass over to Gonzalo and Christian this morning and let them present.
Thanks so much, Damien. So good morning, everybody. Good evening for Christian and me. We are broadcasting from Quebec City in Canada. So welcome, everybody. So my name is Gonzalo Mora, and I work as an international instructor for Festo Didactic in Quebec City. And tonight I'm going to be hosting this webinar in company of my colleague, Christian Remillard, that he's going to present himself. Christian, your turn.
Thank you, Gonzalo. So good morning, everybody. Yes, I will be here just to support Gonzalo, and as a moderator, he will be doing most of the presentation, but I will be here to answer your questions and watch if anybody is raising their hand. So by the way, if it's your first contact with the GoToWebinar platform, you will notice that somewhere in your interface, you have a little a hand icon that you can click on to raise our attention. So you just click on that, and I will see that somebody is asking to ask a question or to, of course, to interact with us. Of course, it will be purely a textual interaction because with the 200 people we are expecting tonight, we can't have everybody speaking, but please feel free to use the chat box or the question box to put us to ask your questions, and I will be a pleasure to answer. So have a good presentation with Gonzalo.
Perfect. Thanks so much, Christian. So let's wait maybe 1 or 2 minutes so we can have some more people getting in. Meanwhile, I'm going to pull out my initial presentation.
So I can see that Mr. Ahmad Kamara has raised his hand. So please, if you want to ask a question or say something, just use the chat box or the question interface, please.
Okay, so let's get started.
In fact, Gonzalo, would you like to start with the little poll to know if the level of knowledge of everybody on LVSIM as we start?
Yep, we can start with a little poll. Hopefully it will work. It's a little bit tricky. Sometimes it works, and it's launched.
So we just ask you to please answer to this question that appears on your screen. We know that some of you will not be able to answer. We're sorry about that. The GoToWebinar seems to have an issue with the feature, but please, for those of you who are able to click on an answer, it will allow us to get a feel of your starting level of knowledge of the tool.
Yep, right now I see it is working, and I see the votes coming in. Yep, 47% of the audience has vote. 51. Wow, impressive. Yeah, it's working really well.
Well, you see, 50 is about what I got this morning. So, yeah. Oh,
now 60.
Getting better.
Okay, I think we get up to 60%.
Yeah, that's
so
good
I
enough.
Will close the poll
now.
And we will start with the system. Okay, so what we have in the screen right now is the Electric Power Technology Training System, the EMS that we call. And as you see, we have a working station with modules that we can insert in our working station to configure the station the way we want to be able to teach the subject that we want in our way. Plus a computer that is running a software in which when we can see some meters, some graphs that is connected to the data acquisition. So from this equipment, that is a real equipment, we create during the development of this equipment the simulator that I'm going to present you tonight. Well, today in the morning. The original system was designed and the first model was built in 1957 and has been evolved during the years. So now we have a very complete system that will allow you to teach a lot of topics of electricity with a very good level of comprehension from the students because it's a hands-on. So how does it look like a lab, the concept that Festo has? So we're going to have these kind of stations to work with the students. We're going to provide working manuals to the students. The software that we see in the back in the TV with circuits, diagrams, and controls, so we can change a lot of parameters and make the system more flexible and more visual. One of the problems that we have when we teach electricity and electronics is that sometimes most of the things that are happening are not visual and may get a little boring. So now we're bringing life and movement to the electricity class. We see a smaller system on top of the table that looks just like the simulator I'm going to show you. In the back, in the corner, we see the motor control module. Both of the systems can work together or as separate units. So here in this slide, we have a small sample of what we can provide as training equipment for electricity. Our electricity training program, we may start in the top, in the gray box, that is DC power electronics. And we can build our way down up to, for example, the principles of double-fed induction generators, the smart grid, the StatCom. All these boxes have been developed, and there's a full course behind each one of these boxes. We can see that here, the boxes, they have kind of a prerequisites. These prerequisites are a logical knowledge that you should have before learning one of these boxes, but are not required. In the case you're going to assemble a lab, you may select only the boxes that you need, and the system will gather the right modules so you can teach all the subjects the way you want and in the order that you want. Now we see some boxes that are in red. These boxes that are in red are the modules that we have in the simulator. So all the courses behind the boxes in red can be done either in the real equipment or in the simulator. We don't have power electronics, thyristors, and for example, the double-fed induction generator. We don't have those modules yet, but they will come in the future. But with the offer that we have now, we are going to see how powerful is this tool and how easy it's going to be for you to teach electricity in a distance way, taking a little bit of the advantage in between quotations of the coronavirus that we're living now. So the lab vault simulator for the electromechanical system is LVSIM-EMS. That is the software that I'm going to present tonight. It is a virtual environment, is a virtual lab running directly on your web browser. You can be either online or offline. So right now I'm going to switch off my screen and we're going to jump directly to the software. Meanwhile, I do the switching. maybe Christian can take a look to the questions, or if someone raised a hand, and answer those questions.
Yes, no questions up to now, Gonzalo. Won't be long.
Well, in my previous days, I was a teacher, so when there's no questions, it frightens me, because there's two answers. Everybody understood everything, or no one understood nothing.
Or nobody is listening.
Yep. So hopefully we're in the first case.
Yes.
Okay. So now I have opened my simulator. As I told you before, we have the simulator. Here we can see in the address localhost. So I'm going to run in my local software, but the software that you are able to use now is this one. It's exactly the same software, but it's fully web-based. Here, you're going to enter an access code, and you unlock the software because that's the license, and then you have exactly the same functionalities I am going to show you tonight. Until the end of June or July, maybe Christian can help me with that, we're going to give free licenses to support all our schools with all their electricity teaching.
I think it's end of June, so until July.
Yeah, perfect. So let's get started. This software can be configured to fit your network requirements. So we can feed it 50 Hertz, 60 Hertz, and the different voltages that we may use locally. So we have in the right part, this big black box with gray squares is the simulation of the module. And in the left, we have this list. Let me make it a little bit bigger. Yep. So you can see better. So here we have modules. For example, we have the DC motor generator, and we have here a number, 8211. These numbers are the same numbers that we have in the real equipment, because later, when we go through the manuals, we're going to see that we're going to fit the manuals with kind of a recipe that we're going to find in Appendix A that shows us what equipment we need to install in our station to be able to perform all the exercises in one manual or one particular exercise. So let's start with the modules. So I'm going to go down, and the first module that we need is always the power supply. That can be placed in any of the boxes. And I'm going to bring a small motor, a DC motor generator, and let's take a closer look to them. Okay, so here we have the motor and the power supply. In the power supply, I have, in the first big square, I have voltage, 3 lines, neutral and ground, 240 or 450 volts, depending on what we're measuring, line or line neutral, fixed. This comes directly from the wall. Then in the next one, we have the same thing, 3 lines, neutral and ground, but now we have from 0 to 240 or 450 volts with 3 amps. This is going to be commanded with the knob. To get a very precise movement of the knob, my trick is get into the arrow, wait until the mouse changes, then I move the mouse away, and I have to make a very large mouse movement to make a very small turn in my knob. If I turn on my power supply, I can see here, right next to the 3 lights L1, L2, and L3, that I have a voltmeter selector. So dragging with the mouse, I can select which pair of terminals I'm going to read. In this case, if I go closer, is going to be terminals 5 and 6. So as I move my knob, I can see my voltage coming up and down. Right next to it, I have a DC power supply that also goes from 0 to 240 volts. That is going to be commanded also with the voltage control knob. We don't have a separate control for the AC and this DC power supply, so both will be controlled simultaneously. And then we have a fixed power supply, also DC current. All the modules in the real equipment are rated for 200 watts. So all the modules here in the simulator also they have 200 watts. So you are not limited to the exercises that we propose in the manuals. You can do other kind of exercises if your circuit is logic will work. So how do we make connections? Here in the upper right part of the screen, we have this red box that says wires color. Here I can choose the color of the wires I will use. So we're going to make the first exercise that everybody has made when we start learning electricity, that is how to make a short circuit. So we're going to connect neutral with line, and the system gives me a warning. You're connecting and your power is on. So I have to switch my power off. I can play with the length of the wires. To make any kind of connection, I will click on the terminal and drag my wire to the next terminal. If I want to delete the cable, I will right-click and delete it. If I need to put a second wire on top of the first one, I will double-click and then drag to the terminal I need. Okay, so let's try our short circuit to see how it works. So now I have power on, my short circuit is finished, and I will start giving some power. So let's wait a little bit, and we see that the reset button has become red, meaning that the breaker has popped. So I have to turn off, get rid of my problem, press my reset button, turn back on, and I can see that now my power supply is working back again in a normal way. Any questions about the power supply?
None that I can see for the moment, Gonzalo. We only had a couple of questions about the dynamometer, which we will get to in a moment.
Yep. Okay, so now we have here the DC motor generator, and we have several other motors in the list that we can use. So I'm going to use the DC motor generator just like an example. So all the motors, we can right-click and lower the front panel. In this case, we have the motor, we have the pulley, and we have the bearings for the belt tensioning mechanism. And here we have a white button. This white button is the same kind of button as the reset button that we saw in the power supply. So if there's a problem in the connection of the motor, we will pop the breaker. And here we have the connections. All the connections are, let's say, digitally silk screened, because the originals are just silk screened. So this is digital silk screen. And we have here numbers and what kind of connections we're going to do in each one of the terminals. All these numbers will be reflected in the manuals, so we can follow exactly the same connections, following even just the diagram or the numbers for beginners, and they will be able to connect the motor. So let's make a small connection to see how it works.
Do you want to bring up the schematic, Gonzalo?
Yep, I'm going to bring up the schematic.
By the way, if you look in your interface, your GoToWebinar interface, you will be a handouts section. And if you unfold this section, you will see that we provided you with a few handouts. These schematics are part of the provided handouts, so you can refer to that while we do the presentation. And know that these schematics are extracted directly from our manual, so that's exactly the kind of circuit that the students and yourself would have access to try out the exercises with the system.
Okay, so while it's a little small, I don't know why it is so small. Let me see if I can make it larger. Yeah, perfect. Well, a little bit less. So we need a variable power supply. We have to go from the positive to the terminal 5, then to the terminal 1 in shunt. We go through the motor, terminal 2, back to 6, and to neutral. That will be the first step. And the second step, it says we have to use a brake and measure the torque and angular speed of the brake, and we have to make a mechanical joint. So this will be the exercise. So hopefully I remember. So it said to number 5, and again, I'm a really bad guy, off. To my motor. Now I'm going to change my color, something a little bit lighter. And then from this one here, and from neutral back. So I just completed the first part of my exercise. I'm going to make it smaller, and let's run it. And because my knob was already with voltage, we saw the motor start turning. So I have now 0, and my motor will start turning and increasing its speed. We did program the inertia. So sometimes you may see that the motor will keep on turning after we make a wrong connection or we change something. Okay, so now we make the first connection with the motor and the power supply. Now we're going to introduce our next element. Let's make this a little bit smaller. So we have here the 4-quadrant dynamometer power supply. And let's take a closer look to it. So what we have behind the front panel, we have a DC motor mounted on this base, but underneath this base, we have a lot of power electronics to let us control the motor. But the circuits were already so complex that we said, okay, we have something really powerful here, so let's make a flexible power supply. So that's why we have combined it in the same device, a 4-quadrant dynamometer and a power supply. So let's get even closer. there. We have two operating modes for the 4-quadrant dynamometer and power supply. We can operate it as a dynamometer or as a power supply. In the dynamometer mode, we have the function button, the start-stop button, and the command knob. I'm going to turn it on. In the real module, we have to connect it here to the wall, but in this case, it's pre-connected for us. So here we have the measurements of speed, torque, power, and the status of the system. In this status, we have it's stopped or running, what kind of control we have, either manual or computerized, and the function. In this case, we have some acronyms, and people, they love acronyms, so it's 2QCT, so it's 2-quadrant constant torque brake. All the measurements that we're going to have here in speed, torque, and power, they're going to be the measurements from the machine that is connected to the dynamometer. Friction has been compensated from the belt and the bearings, so these measurements are direct measurements from the machine under test. Each time we press the function button, we're going to change of function, of course. So now we have a clockwise prime mover or brake, counterclockwise prime mover or brake, clockwise constant speed prime mover or brake, counterclockwise constant speed prime mover or brake, positive constant torque prime mover or brake, a negative constant torque prime mover or brake, and we finish our cycle again with the 2-quadrant constant torque brake. I'm going to change the function for the prime mover, and I'm going to press my start button. So now I see that it's started in manual, and with my command knob, I'm going to start turning my command knob, and we can see behind that my motor starts turning. So I can choose what speed I need or what condition I need with my knob. Another way that we can do it is, for example, let's say I want 1500 RPM, but I don't want to use the knob. So I can stop it and tell the system, okay, I need 1500, and then start it. In this case, because we have the prime mover brake, not the constant speed, will not arrive exactly to that speed that I requested. Okay. So I'm going to put this down, and let's see what we have in the lower panel. In the lower panel, I have a command input from 0 to plus minus 10 volts that will replace the command signal from the knob. We have an shaft encoder outputs A and B that will be transistor to transistor logic. We have a thermistor input, and we have analog impulse, torque, and angular speed. So now we see that we have these two jacks that were represented in the diagram. So we may need to connect those to something. In the power supply mode, the function button and the command are exactly the same, but let's go through the functions to see what we have. We have a positive voltage source, negative voltage source, 50 Hertz power supply, 60 Hertz power supply, and we cycle back. Our terminal, that will be the live terminal, phase or positive, and my neutral or my reference, depending if I am in AC or DC. Later, in the future presentations from the webinars that we're going to have next week, we're going to show you more features about the 4-quadrant dynamometer. So now I'm going to reduce this a little bit. So I need to join these two mechanically. So I'm going to lower the front panel of both of them. There's two ways to put the belt. I can click when my mouse is in the center of the shaft. And I will put the belt. Or I can click in the top and happens exactly the same thing. Doesn't matter in which position I have the motors or the dynamometer. Both they have the tensors, so they can be in the left or in the right and will work in the same way. So basically we have all our connections right now. And let's start making some measurements. To make some measurements, we have these two multimeters. So, well, let's put it here. This multimeter is looking really weird. Let's look at the other one. Normally, I should see here some letters. I don't know why they are not there.
Yeah, that's weird.
Tell me voltage, but if I'm right, I think this is voltage. So let's connect neutral and this one. Yep, that was voltage. So we can connect the two multimeters and start making measurements directly in the machine, same as we will do it in the lab. If we move the multimeter, the connections will follow. Same will happen if we move. For example, I move the power supply here, all my connections will follow. That's a very nice feature that we don't have in the real one. That will be a very good improvement. And now the power supply does not want to come up. Whoa.
Huh?
That's weird. I'm going to delete my power supply, and I will bring on another one. Okay. So we need this wire, and we need the red wire, and we're done. Okay, so we were back where we were. Do you have any questions to this point?
I only had one question about the dynamometer and asking if it was, well, any of our rotating machines, asking if it was possible to measure the rotor angle. And unfortunately, sorry, I thought that you meant the phase shift or the speed of rotation of the axis of the motor. So this, of course, we provide the input for, but the rotor angle cannot be measured with the dynamometer because we're not in a stepper motor situation here. We are simply with a DC motor acting as a dynamometer connected to any other machine you want to put under test. So we have no way to measure the rotor angle itself. But the speed and the phase shift between our voltage and current, but of course it has no rotor angle, sorry.
Okay, so let's continue. Now we have the new module that I just pulled out, is the data acquisition and control interface. So here we have basically 8 multimeters, 4 voltmeters, 4 ampere meters, all of them, they are opto-isolated. The common connections are only for each line. So if we want to measure, for example, the voltage 3 lines through the neutral. We have to connect all these 3 to the neutral. Or we can make any kind of measurement. For example, I can measure here AC, DC, and another source. It doesn't matter. It's like having 8 different devices built in one single module. So then we have here analog inputs with the analog reference in white, digital inputs for an encoder, for example, or a synchronizator with its reference, analog inputs. Here we can see that we have 8, but number 7 and number 8 are dedicated to measure torque and angular speed. Then we have digital outputs. We have a DB9 that will be connected with another module that will be, for example, the IGBTs and the thyristors that we have only in the real equipment, not in the simulator. In the lower part, we have the power input with 2 jacks. And then we have here a USB port. Of course, here the USB port is already pre-connected to the computer. If I go back to my power supply, underneath the main switch, I have this small panel that says 24 volts, 3 amps. So I'm going to drag a cable from here to the power input, and then I will turn it on, and I can see that the LED of the data acquisition turned on. I'm going to move this cable away there, and now my data acquisition is on and ready to be used. So I'm going to make basically 2 connections just to show what we can do with the measuring system. So let me make this a little bit smaller, and I'm going to use any color to make this measurement. So I'm going to use E2 to measure simply the AC current, and E1 to measure my voltage. Okay, so I think we can start this for now. Let's put this to turn. Go to Dynamometer. Give it full voltage. And let's start. And I can see here that I am loading my machine. I have the speed, have the torque, and the power that is present during my experimentation. So I can change my physical conditions, and I can monitor in my data acquisition. So right now I'm going to try to split my screen in 2 parts so I can show you the meters. Okay, so excellent. I have here my meters. And let me reduce my machine to something more visible. Okay. So we have to turn on the power for the DACI. And here we have my meters. In total, we have 18 meters that we can turn on or off. And all these you can configure and you can make them measure what you need. So in each one of them, we can have voltage, current, power, efficiency, impedance, power factor, frequency, energy, reactive power, integral, torque, speed, and phase shift. And for example, in power factor, we're going to choose which combinations of voltmeter and amperemeter we want to use to measure the power factor in a specific place. Also, sometimes it is desirable to have a voltmeter with a needle. So we can provide that in this case. So I'm going to apply it. Okay, and now I have here E1 digital, E1 with my needle, and also a digital indication. To start grabbing the data, I am going to press the double white arrow that is continuous refresh. And I can see here that I have my values directly. And I'm way over what my, okay, that's better. So now I have configured my meters. I want to measure the angular speed and the torque that comes from the dynamometer. So right now I don't want to stop all the machines, so I'm going to drag the cables, but we're going to have the warning message. Now, it seems that I need to come back to this screen. So torque, let's make them and now I need a white one. Okay, my connection is done. So here I have the meter number 6 and the meter number 12. And now we have the torque and the revolutions per minute that we have in my motor. So I can make any kind of mechanical change and I will see my meters getting the data on real time. Any questions?
Yes, in fact, I have a few questions, Gonzalo. So sorry, I answered some questions privately, some questions to all the groups. So I will just make sure that everybody got the questions and the corresponding answer. So I already answered the question about the rotor angle. I have a question here from Mr. Yassim, how to change the AC network from 120 60 Hertz to 240 50 Hertz. So it's in the settings. If you can show how to do that, Gonzalo.
I will show that right away. So tools and options, here we have the AC network and we have the choices. So apply, okay, and everything will be reset. And now we have other voltages. And if we get close to our machine, see, we have here 220, 380. So even the digital silk screen in the facades will change. So now that we have our automatic data, yes?
I still had a couple of questions, sorry, Gonzalo. I had another question about, is it possible to lock the rotor? So as I answered, yes, it is possible. In the real physical system, yes, it is. And as I answered privately, it's possible to lock it without any harm to the motor because our motors are really sturdy. And same thing with the simulator. Yes, you can put a torque high enough on the rotor that it will stop. Another question from Mr. Yassim was about is the license available also for the instructor with the module with the answer schemes? So we do provide the licenses to instructors, of course, and as we will see later on, you do have access to the manuals, the student manuals. I don't know if we do provide the instructor manuals, Gonzalo.
We don't provide the instructor manuals here in the software directly, but you have to make the request directly to your Festo local company, to your Festo dealer, and he will be able to provide a watermarked copy of the manuals with the answers for the same manuals that you have here in the simulator.
Okay, thank you. And finally, the last question was about the maximum voltage that can be displayed on the power supply voltmeter. We can see on the screen there that the maximum is 250, and of course, phase-to-phase voltage is 400. So the question is it possible to have this voltmeter go above 250? I think that this analog voltmeter is fixed and it won't go above 250, but as you just saw, typically you will be using the voltmeters in the multimeters here to look at your values, and these are not limited, of course.
Okay, so let me stop this.
We have 13 minutes left, Gonzalo.
Yep. Okay. So the last part is, now we have our meters running. Now we're going to have the automatic data collection. So let me make this larger. We don't really need the meters now. So we're going to click here on this data table. It looks like an Excel sheet. Here we have the record settings. So the metering window has to be opened and has to be already configured the way you want. And then you will have access to the same meters that you have in your metering window. So in this case, we want this one, this one, this one, and we have these 2 voltmeters. Apply, yes, okay. And now here we have the 2 voltmeters, the torque, and the revolutions per minute. So we can start making our data collections manually. We change, for example, voltage here, go back to the table, and we make our data collections in that way, or we can make it in an automatic way. We can choose the interval between records, seconds, minutes, hours. For example, let's make something kind of quick. And let's make 25 records, okay? And then we start and we have the automatic data collection. Well, in this case, I'm not moving anything, so we'll have the same data always. Of course, we can erase some data or all of it. I'm going to recollect again my data, and we can make a graph. So you can choose E1, in this one E2, the colors. So we will have the graph of the data we just collected. So there's only like 10 minutes left, so I have to speed up a little bit. If I go to the help, I'm going to go to manuals and exercises. And here we have all the PDFs of the exercises and the manuals that you can use. For example, we have power factor correction, AC transmission lines, power circuits and transformers, AC, DC motors and generators, DC power circuits. In some manuals, for example, in permanent magnet DC motor, let me make it a little bit larger. It says, in exercise 2, the shaft of the permanent magnet DC motor cannot be rotated manually in the lab volt simulator, of course. So basically, all the exercises that we do in the real equipment are going to be the same exercises, and they're going to be done in the same way as in the simulator, except for the one that I show you, 1, 2, 3, and 4 steps of all the manuals. That's very few that cannot be done directly, but there's going to be something to perform this in the simulator. So for example, if we go...
Sorry, Gonzalo, since you just spoke about this limitation of the simulator of not being able to hand move the shaft of the motor, I just had a question about is it possible to simulate the manual locking of the shaft motor that we can do on the real machine. So, well, this answers the question. No, it's unfortunately not possible in the simulator to handhold a shaft of the motor.
Yeah, I'm pretty sure the programmers are thinking about to build up a real hand in the simulator so we can hold it. Or a hammer can do it. I'm a mechanical engineer, so for me, the hammer is a very, very useful tool.
Not as good on a computer screen, though.
Depends. Okay, so let's take a quick look of what are the contents in general. I'm going to go to through the body of a manual that you will receive so we can see what is the structure, the academic structure of the manuals that you will find in all the manuals that we use in the EMS. So here we have, in the exercises, we have a discussion of the theory, and then we have a procedure. So let's jump just to exercise 1 as an example. Here we see all the boxes that we saw in the beginning of my presentation about the knowledge. And here we are in this box, 3-phase AC power circuits. So let's go to chapter 1. Okay, exercise 1. 3-phase circuits. So we have an objective, what we want to learn, then what we're going to remind our students in the theory. Then we start with the theory. We're going to use colorful graphs. We try to make our explanations short enough, but with the right deepness. So the students will get exactly what we need them to remember so they can make the lab in a logical way. So here we have some Y and delta configurations, some circuits, and of course, diagrams, equations. And when we get to the equations, we're going to present the equation and then a list with all the variables, what they mean, and what units they use. Now we get to the procedure. In the procedure, we're going to have, in this case, 4 main parts: setup and connections. Then we're going to make phase and line voltage measurements in the power supply. Then voltage, current, and power measurements in a Y connected circuit or in a delta connected circuit. So now we go to the steps. And here in the first step tells us, refer to the equipment utilization chart in Appendix A. So we're in page 17. Let's go to take a look to Appendix A, how it looks like. Okay, so for exercise 1, we need 1 workstation, 8131, 1 resistive load, 8311, and so on. So here we have exactly what kind of modules we need to install in the simulator or the real equipment to be able to perform the exercise that we want. Each one of the exercises can be done in around 2 hours, including reading all the lecture of the theory and then performing the steps to make the exercise. Normally, in 1 hour 45 to 2 hours, that is a classical lab period, the students are able to fulfill all these basically practice guide that we have here. So we go through the steps, we're going to build up the circuit, then we start answering questions or getting data. In the teacher manual, what you're going to have is exactly the same contents, but underneath, for example, step number 7, we're going to have a red square with the answers that we have for the same exercise and in the same condition. Some more questions, more data collection, change the circuit. We keep on interacting between the system and the book. And at the end, we're going to have conclusions. We have the conclusion of what we have learned, and then review questions that can be a small quiz after the lab. So this structure is going to be repeated over and over into the manuals. So I'm going to close this, and I'm going to make this a little bit smaller. And now I will give the word to Christian to see if there's some questions about the system, or if there's something else I can tell you today in the morning.
Yes, I have some more questions, Gonzalo. So, okay, let me see, I will tackle them in order. So I have one question about the possibility of extending the workstation space to use more modules. In fact, that's a really interesting question. It's the first time I hear this one. And you're right that in a simulator, that's something we might expect, but except that our simulator is so close to the reality, in real life, you cannot extend the console, and you can't either in the simulator. And unfortunately, in the simulator, it's not possible, as in real life, to have two consoles side by side so you can have more modules, except that this would be really to build your own homemade exercises, because all of our exercises typically will use only modules that can fit in a single console. So the exercises that are defined in our manuals will all fit within the space of a single console. But I can understand that you might have some more some more additional requirements for your own exercises. I had also a question about how to select AC and DC power supply. I'm not sure if I hear the question well. It's if it's on the power supply itself. You will see that we have, Gonzalo will show you that we have two sets of outputs on the power supply, the AC outputs, which are the two on the left, and the DC outputs, which are the two on the right. So this is fixed three-phase output.
AC, DC, and DC.
Exactly. And if you meant in the, sorry, just to conclude, maybe they were asking for the meters. The question maybe was about the meters. So in the meters, you have a button to indicate if you want AC or DC, to measure AC or DC, just like that.
Yep. Something I want to tell about the simulator is that you have a big advantage over the real equipment. Here we see that the 4-quadrant and the DACI are grayed out. So it means that you can use it only once within the system. But for example, if I want to use this small power supply, I can have 1, 2, I can have as many as I want. So I'm not limited in the amount of equipment in these ones that they don't gray out to build a circuit in my console. So for example, if you want to make just a circuit with resistors, inductors, and capacitors, you can fit a lot of them and you can make a very complex circuit. So you have that advantage because in the real ones, normally you have 1 or 2 of each modules, and then you are limited to what physically you have.
I have here another question about, is it possible to do experiments related to switched reluctance motor? I fear that we do not have the same nomenclature in North America for these types of motors. So how would do you know these motors, Mr. Aduru? Would you know these motors by another name? Are you talking about the stepper motor or something else? Because typically reluctance motors refer to stepper motors. You can maybe use the chat box to answer my question, just to tell me if the switch reluctance motor you're talking about is a stepper motor. Meanwhile, I will look at other questions that we have. Did we answer them all? There was a question from Mr. Yassim, if a vector control drive were available in the simulation software. I don't know if you were there from the start, Mr. Yassim, but initially Gonzalo mentioned that the courses that are available on our simulator are restricted to mostly the electromechanical courses. So basically no power electronics courses are available. We don't have any IGBTs or thyristor modules in the simulator. So it's not possible to do anything related to power electronics like speed vector, like vector drives or smart grids or anything like that. And I have another question here. Renewable energy labs seem currently not available in LVSIM, indeed, such as DFIG or small-scale wind generation. So yes, any of the renewable energy is not available. Neither is anything related, again, to power electronics. So since part of our renewable energy packages in the real system require power electronics, like the home energy production course, for example, these are not made available. I don't know why they took the decision not to include wind power and solar power when they developed that. That would have been a good addition, but for the moment, they're not available. Mr. Chu, you're right.
Okay, so we are getting basically to the end of our presentation. But we would like you to invite for next week that we're going to provide several webinars. And in this time, we're going to use the simulator to go through subjects. So we're going to go through different subjects, such as power factor compensation, generator synchronization. So we're going to learn how to make these kind of exercises within the simulator. So hopefully for the next days, you will receive another invitation so you can join us in this webinar. So do you have something else to say, Christian?
Well, I don't see any other questions coming in, and I don't see an answer from Mr. Aduru about the reluctance motor, so I guess we will have to answer that at another time. So thank you all for being with us. Yes, to end this webinar, we would like you to answer 3 more polls to help us see if our webinar was effective. So if you could please answer to these 3 small polls now. And again, for those of you who were not there at the beginning, I know that some of you will not be able to answer these questions. The software seems to have a problem with some computers, so some of you might not be able to click, but we are collecting the answer from those who can. Okay, we have another one for you if you want to stay with us for 1 more minute. Excellent. And one last one to finish. So again, thank you for participating, and hopefully we'll see you next week in our advanced webinars using this platform to show you that we can do more than just connect wires and learn about the interface, but we can also actually teach concepts as you would do in the classroom with your students. Thank you for participating. Thank you, Gonzalo.
Thanks, Christian. So hopefully you have enjoyed this small presentation, this small webinar, and we're looking forward to see you in our next presentations next week. Please keep safe. Have a nice day. Thanks so much for attending.
Last word from Damien.
Thank you, guys. And if you've got any offline questions on any of the topics covered today, or want to see any particular topics covered in the future webinars, if you can please contact us. Thank you all.
Absolutely. You have our emails. Send us your comments and questions anytime. Thank you.
Thanks so much.
Have a good day.
Bye-bye.